Hello, everyone. Welcome to CS 340. I'm your host, Frank. This is your co-host, Payman. Today, we're going to talk about nonlinear regression, and it's fall 2020. So last time we talked about linear regression, we talked about linear models where we expressed our outcome or output yi as a linear combination of our features xi1 to xid weighted by some model parameters, right? And we said that we could write this down in a bunch of different ways. We can write this down as an explicit sum over the dimensions of the weight of that dimension times that parameter of, or so excuse me, the weight or parameter of that dimension times the input, for example, I in dimension j. Or we can write that down as an inner product between a parameter vector w or weight vector w and our example xi. Okay. The idea is, multiply feature xij by weight wj and add them up across all j to get yi. Okay. And we said, our little program, which we need to run in order to make a prediction. I'll look at the bottom right here and say, in order to make a prediction, we need W transpose. So that when we get a test case x twiddle I, we can take an inner product and make our prediction y hat I. Okay. In order to learn this parameter vector W, we need a loss function. And we talked about least squares, or the squared error function here, where we sum over all the data items the difference between our prediction, W transpose xi, and the true value, yi. Square the difference, add them up, and this is our loss function or objective for learning the parameter W. Okay, cool. So we're going to move on to actually solving this today. And in order to do that, we're going to reintroduce or bring up some notation that we'll use more or less for the rest of the term. So when we solve the d-dimensional least squares problem, we're going to use matrix notation, right? So W, our weight vector, parameter vector, whatever, is a d by 1. So d in this dimension, 1 in this dimension, vector containing weight j, wj, here, wj, in position j, 1, 2, up to position j. Okay, cool, fine. Y is a column vector, which is n by 1, containing the target yi, or output yi in position I. And use xi as a d by 1, as a number of parameters by 1 vector containing features j, right? So this is xij in general of example I. And from this point forward, basically we're just going to use column vectors. Okay, so everything that we talk about are column vectors. Okay. So X, our data matrix, is a matrix with xi transpose in row I. Okay, so this is x1 transpose, right, as we show here, and x2 transpose, so on and so forth. Okay, fine. Very straightforward. That's the notation we're going to use. Fine. And our prediction, for example, I, is this weight. So W transpose is going to be 1 by D, and then X is going to be D by 1. We multiply these two together and we get our 1 by 1 output. Okay, cool. So our prediction, for example, I is given by the scalar W transpose Xi. Okay. And because W transpose Xi is a scalar, we have that W transpose Xi equals Xi transpose W, because of course, if you have a matrix with one element, the transpose of that matrix is just that matrix, okay? or the transpose of a scalar is just a scalar. Okay, scalar is just a 1 by 1 matrix. The predictions for all I, right? So this is going to be an n times 1 vector, right? Is the matrix vector product xw, right? So, yeah. So I guess we'll just do y hat equals this, right? So, you know, this W matrix goes in and hits this xi, and that produces the corresponding entry of our prediction matrix, which is n by 1. Okay. Cool. Pretty straightforward. Nothing super fancy. The residual vector R here gives the difference between the predictions we make, y hat, and y. And this thing is also n by 1. Okay. And our prediction, which we just wrote down last time, y hat is just x times w. The difference with the true label is just minus y, right? And if we plug in each entry the definition of what xw is, it computes the inner product between w transpose, but you can compute the inner product between w and each individual x. And these are all of the individual labels, right? Okay. Obviously, we can take this minus out and move it inside. And R2, right, the second element of this n-dimensional vector is just the prediction error for the second example. Okay. So if you look at what our loss is, our least squares loss, right? Our least squares loss, we said we're going to sum over n over all of the examples of the residual for that example, right? So W transpose Xi minus Yi. Then we're going to square that, right? Fine. So since we just defined what the residuals are, or like R1, whatever, right? So we just defined what this is. That's just the residual for the ith element squared summed over n, right? You can obviously, the square is just, you know, it's just the sum over Ri times Ri. And that's just the inner product of R with itself, okay? This sum, which is just the norm of R, the 2 norm, this is the default 2 norm, the 2 norm squared. So remove the square root from the norm, okay? And again, if we remember what y hat is, right? This is just y hat here minus y squared, okay? So these are all kind of the same thing. But this is ultimately, this thing right here, that's our objective function. That's the loss that we're seeking to minimize in norm matrix notation. Okay. So the 2 norm of x times w minus y squared. So we have this, right? Same thing. Nothing new here. We write the vector predictions y hat matrix vector product. That's what we just did, right? We can write down the loss like this. That's what we just did. And what we do is that we use this notation to derive the d-dimensional least squares w. Okay. And we're going to do this by setting the gradient function. We're going to derive the gradient function, so the gradient of our objective with respect to w, such that we can evaluate it at a given w, set it equal to 0, and solve for the resulting vector w. Okay. Now, the fun thing is that linear algebra and multivariate calculus are prerequisites for the course, so we actually don't have to spend a lot of time on this, thank goodness. But it's worth just reviewing a couple of things, just so the notation in the next slides isn't unfamiliar or overly unfamiliar. So let's do a quick review of the linear algebra operations that we'll use when we're doing this, and then these we're just going to use quickly when we do stuff in the rest of the lecture. So let's not do pirate speak. If A and B are vectors and A and B are matrices, then provided that A and B are compatible, right? This is a scalar, right? This is the same scalar. And there's a couple of ways that you can get at this, but it's sort of obvious that if you take the inner product of two vectors, it doesn't matter the order in which you take the inner product. Right? We know already that the norm squared of a vector A is just the inner product of the vector with itself. You should remember straightforwardly that transpose operations distribute, right? So A plus B transpose is A transpose plus B transpose. You might not remember, although you can look it up in the matrix cookbook or in your linear algebra textbook or whatever, that the product of matrices that are again compatible, A and B, that product transposed is equal to B transpose A transpose. And of course, the first, outer, inner, last rules of distribution and additivity and so on and so forth apply for matrices as well. So the matrix A plus B times the matrix A plus B is equal to the matrix product of AA plus BA plus AB plus BB, right? That's sort of clear from just standard rules. This one is a little bit less obvious. It's just like one step that you have to do. So do it if it's not obvious to you. But this whole thing is a scalar, right? So we can write that this whole thing is equal to A transpose AB transpose, right? And then if you apply this rule right here, you get B transpose A transpose A transpose, and then you're done, right? Okay, so we use this a fair amount. It's kind of hidden in one derivation, but that's something you should know and be able to demonstrate easily. Okay, so like I was doing on earlier slides, already kind of as a hint, right? It's a really good idea to sort of do mental type checking when you're doing matrix vector algebra, right? So you need to know that this thing is a scalar and that these things have dimensions that are compatible, right? If A is n by 1, and then A transpose is 1 by n, and B is n by 1, then the whole thing is a scalar. Everything is compatible, so on and so forth. So we have to have non-traditional examination structure in this course, but I can tell you that if we did have traditional examination structure, it's very, very likely that mistakes of compatibility would show up on the examinations because like 50% of the examinations have mathematical expressions involving matrices and vectors that are completely incompatible. Okay, the steps are like every individual step is laid out in the post-lecture slides. But what we're going to do now is we're going to look at our least squares objective, which again is just this, which in matrix vector notation looks like this. And note we've stuck the half on here, but we know that doesn't matter. We just sneakily put that in there, right? Doesn't matter, it doesn't change the objective. I guess the one thing to point out is this whole thing is a vector, right? We know this already. We already know what's going to happen. So this is the same as, right? So that's where the transposes are going to come from. Anyway, so if you distribute the transposes inside here, which I can't do without, let me get rid of this. And then you do first, outer, inner, last, you get an expression that looks like this. Okay. Should be pretty straightforward. You can see there's the W, here's the W transpose, X transpose, here's the XW. There's a W transpose, X transpose from here, and Y from here, and so on and so forth. And then the 1/2s come in here, And the 2 cancels in the middle because there's 2 copies of the same thing, although you have to do a transpose trick to get that middle term. Okay, anyway.
Why is the 0.5 there?
So Siddharth, I said it quickly, which is that this f of w, whether it's f of argmin w of f of w equals argmin w 1/2 f w da 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 da. Okay, so we're putting the 1/2 in here for mathematical convenience, basically. Constant doesn't change the answer. Makes, yeah, exactly. That's what I said. Thank you. Cool. Okay, so what size is x transpose x? Okay, Heyman, what size is x transpose x?
Scalar.
Hey?
It's going to be scalar, right?
No, x transpose x is a matrix. All right, so everybody gotta pay attention. So x is n by d, right? So x transpose is d by n.
Oh, it's going to be n by n.
D by n. So x transpose x is d by d. Okay. So this is a d by d matrix. W is a d-dimensional vector, so that's d by 1, and W transpose is 1 by d. So this whole expression is a scalar, right? But the inner thing is a d by d matrix, and this is a d by 1 matrix, d by 1 matrix. So this is kind of like the little type checking that you do to make sure that everything's compatible. Okay, so x transpose again, this is a d by n quantity, y is a n by 1, so this is a d by 1 times d by 1. Okay, great. So this is a vector v. Okay, so everything's looking okay, and y transpose y is going to be 1 by n times 1, n by 1. So we're all good. So this thing is a scalar, this is a vector, this is a matrix. All of the individual terms are scalars. Okay, fine. But if we just pull out this matrix A, this d by d matrix A, and this, I guess, d by 1 vector B in the scalar C, then we have what looks like and is a matrix quadratic form. Okay, all the dimensions match. How do we compute the gradient? Yay, we're almost there. So let's first do it by just being really simple to see why this looks like a quadratic form, right? So if we assume that d equals 1, right, then A becomes a 1 by 1 matrix. In other words, a scalar. W is no longer a vector, it's just a scalar. And this whole thing, all the terms, every single term here is a scalar, right? And if you look at this, this is just a standard second order polynomial quadratic equation, right? And we can compute, we can analytically derive the gradient function, right, which evaluated W gives you the slope of the tangent at that value W, right? Okay. So there are generalizations for these gradient rules in d dimensions, which we expect you to know. And if you can't remember them, look them up in your textbook, or find them in the matrix cookbook, or wherever your favorite place is to find these things. Prove them to yourself again if you've forgotten. The gradient, for instance, here with respect to W, of a constant expression is the 0 vector. Yep. The gradient of a linear form with respect to W is just B, the B vector. So the gradient of W transpose B with respect to W is just B. And the gradient with respect to W of this, the gradient operator applied to this expression, this quadratic form, 1/2 W transpose A W, is equal to AW if A is symmetric. Okay. So with these expressions, we can look up here, right? Okay, so we've got the gradient of this guy, we've got the gradient of this guy, and we've got the gradient of this gal, right? Okay. So You can look up the full derivations for all of these things. They're on the webpage. You can look them up in a million different places, but be aware we're using these rules. Okay. So if you just apply those rules to this expression, then the gradient of our loss or objective, the gradient operator, returns the following function: AW minus B plus 0, noting that A is a matrix, W is a vector, and B is a vector.
Is always symmetric because X time X transpose.
Akeem, that's correct. Yes, good point. Not everybody picks that up, but yes. Okay,
So
Alan.
do we need
the birthday boy? Oh, that's probably almost identifiable. I apologize, Alan, if you don't want to be identified. Happy birthday anyway. Let's yeah, we're going to talk about whether or not we need to invert this or not. You're one step ahead. Let's just identify first that A is this thing, B is this thing, and C is this thing, right? Well, I guess the whole thing doesn't really matter. Okay. So if we plug in the definition of A and the definition of B, right, we get that the gradient, and this is important, this gradient function, you're going to end up using this later, right? So you need to actually understand that the gradient function of a linear regression model with a least squares objective looks like this. Say, for instance, if you ever wanted to do gradient descent or something like that, you want to be able to look back at this and say, this is the gradient, right? Okay, cool. We can do the sanity check. I've already done it like 6 times. So I'm not going to do it again. So these all work out. In other words, at the end of the day, we want the gradient to be the same dimension as the vector. So we want this to be a d/1 quantity. And in fact, it is if you look at all of these, right? So we've got a d/1 quantity. That's good. Now we have to be able to find the critical point. So we want to find the W or set of W's that when plugged into the gradient expression yield the 0 vector, the d/1 dimensional 0 vector. Okay. So we can, move all the terms that not involving W to the other side, right? And now we have this thing, right? And Alan's point is exactly what you'd expect. So the first thing you might think of doing, is, oh, look, if I just do this, right, I'm done. Okay, that's not quite true, and we want to be a little bit more careful about that than about this point than you might do. So let's not think about this right now. If that's okay if A is invertible indeed. But the way we want to look at this is that this is a set of D linear equations, right? And these are called the normal equations. And this is a linear system like you learn in linear algebra, right? AX equals B. And what you should know is that there are many ways to solve this. Standard one is to use Gaussian elimination to solve for W. For our purposes, we're just going to say that this is something that you can call a mathematical software package and just have it solved. In Python, you can solve linear systems in one line using NumPy linear algebra solve. Okay, fine, great. So this gets to the birthday boy's point again, just a little bit, right? The least squares objective is this. The minimizers of this objective are solutions to the linear system that we just derived, right? The following are not, in one case, not necessarily the solution to the least squares problem. So just taking the inverse of x transpose x and moving it, applying and multiplying it, left multiplying it on both sides, only works if x transpose x is invertible. Okay, and that will be true if x transpose x is full rank, and this is going to be problematic when D is greater than N. Okay, so, and that's going to be a case that we're going to be in a lot in machine learning, unlike in statistics. There's a lot of garbage that you can produce, right? Like in exams, this one is one that's written in basically every single exam, right? And you're like, oh, look, I can solve this. I just divide by X transpose X. That is not a thing, right? Barat, yes. Okay, so these are not solutions, okay? These are not solutions. This one you have a little wiggle room on, but again, you don't, these are warnings for typical exams, so that's okay. So Barat, yes, D greater than N, and have that in your mind when we're going through the remainder of this lecture. You'll start to see how this could happen, okay? We should think about how much it costs to solve these normal equations, right? So forming this part, X transpose Y, costs O in D. It has D elements, right? It's a D element long vector. And each entry is an inner product between n numbers. Forming the matrix X transpose X costs O and D squared. We already looked at it and said that's a D squared size thing. And to make every one of those entries, you have to do an inner product between vectors that are n long. Okay. And then solving a D by system of equations costs O D cubed, right? That's the cost of Gaussian elimination on a D variable linear system. Other methods have the same cost, right? So the overall cost is O is order ND squared plus D cubed. And which term dominates depends on N and D. So if N is much, much larger than D, then this term could dominate. If D is much, much larger than N, then this term will dominate, or just a little bit larger than N. Okay. There are some issues with the least squares model that we've talked about. The solution might not be unique. That's not obvious, actually. It's certainly sensitive to outliers, like the ones we talked about. It always uses all the features, which is not necessarily a good thing, although there's an argument to be had that that is what you should do. The data might be really, really big, in particular in the D dimension, right? So you might not be able to even store X transpose X, or you can't afford this cost, whatever that happens to be, right? You might predict values outside of the range of the values that you have yi in your data. And of course, it obviously assumes a linear relationship between xi and y. And we're going to talk a little bit about this today. How do we deal with this? But first, let's think about why the solution to the least squares problem might not be unique. So let's do a little thought experiment and think, well, what if there are two features that are identical for all examples, right? So in other words, if this is the case, then when any solution, I can basically move weight around from one of those features to the other, right? So I can increase weight in one feature and decrease it on the other without changing the prediction. So if y hat I had, like, basically xi1 is duplicated in the data. So pardon the notational insufficiency here, but like we have two copies of the first dimension, the first feature of X, right? I have two weights, W1 and W2, right? Well, if this is a solution, then this is a solution as well, because xi1 is the same, right? So in other words, I can take any convex combination of W1 and W2, and all of those solutions are exactly the same. They'll produce the same minimum value of the loss. Okay. So for example, if W1, W2 is a solution, then just moving everything onto the first copy of X is an equivalent solution. So this is a very special case of features being exactly collinear. In other words, one feature is a linear function of the others. But we should remind you, or we'll talk about this later, any W where the gradient of this objective is equal to 0, in this case, for this model, is a global minimizer of F, right? And that's due to the convexity of this objective, which we'll talk about later. Okay, questions at this point? John, will we have to do these calculations on the exam? I'm not sure. Yeah, I'm not sure. That's the answer. Yeah. If A isn't invertible, can there still be a gradient of f equal to 0? Yes, there can be. Yeah. That's the whole point. You have an equivalent surface. Basically, you have a loss function that has basically a whole plane or surface that's equivalent. So you have a lot. Yeah. So okay, Leo, good question. So outside of the y range, what we're really saying is that there's always going to be some domain of where we actually have xi's, right? And we're going to have some data for each of these, whatever that happens to be. And there is some range of yi's, right? And it may be that, for instance, it doesn't even make sense for there to be a negative output, right? So certainly the functional form of the relationship between input and output, right, is linear currently, right? So it's basically saying, well, maybe actually if we need some nonlinear relationship, we might have to do something slightly different. Okay. Or if we know something more about where it should extrapolate, we would want to put that information in. To what extent can the total cost be improved, or is it pretty much standard? That one, Payment, do you have any idea what that means? I'm struggling with that one.
Not sure.
So I think there's two costs that you could be talking about. The total cost of computational complexity. I see. Yeah, so the question you're asking is an algorithmic question about sort of solutions to linear systems. And the answer is, if there are special cases, if A is known to have a very specific structure, for instance, then yeah, you can do slightly better than that. But in the general case, no, not really. And wouldn't all interpolations have this problem? Unless you happen to know something about nature and the specific form of the family that the regression sort of should be in, then in general, yes, you will have problems with. This is, just to be clear, this is extrapolation that we're talking about. Interpolation is kind of the same thing. It's just making a statement about the value of the function away from the data in some sense. Yes. Cool. Thank you all for involving yourself in the conversation. It helps with the question answering quite a lot. Thank you. Okay, cool. So great. So we've got this idea in our head right now, right? And just to be clear, if it isn't clear already, we've got this idea in our head that we have some input-output relationship, and we're going to model it linearly. Worse, so far, we've only actually talked about models that pass through the origin. We haven't even dealt with like an intercept term that might make the relationship better, right? But we're going to deal with these all in one go right now, okay? So let's think about the relationship between year and athletes going faster, higher, and further, right? So here we have the 100-meter progression of times for men down here, maybe that's linear. The 100-meter progression line for women, it's a little bit suspicious in the 1980s, right? Here's the high jump progression, right? Here's the, for men and women. There we have men on top, I believe. Shot per progression for 2 different weights, men, women again, right? So you could ask, is this actually a linear relationship? Maybe it is, but it actually really looks like there's 2 different linear relationships with a very suspicious kink in the 1980s. Anybody have any theories about why there might be a kink in they changed how they measured. That's, yes, I think I think probably 1985. Well, that speaks well for me and not well for the rest of you, Akeem, if indeed we reached the peak of evolution in 1985. Anyway, beautiful. I think there might have been some drugs going on in the 80s. Not sure, but it certainly seems that way. So the question is, can we, like, what do we do when we have a nonlinear relationship between the input and output in some regression model, right? Which, frankly, let's be honest, we don't know whether or not we have linear relationships in most cases, so we need to be able to deal with nonlinear relationships, okay? So one thing that we can do, and we've already hinted at this, and these are these tan slides. Wow, they actually look tan here, that's great. We can adapt our classification methods to perform regression, right? I just realized something. I'll tell you a funny story at the end if you want about the screen colors. Okay, so we can do a regression tree, which we talked about last time, where we have that leaves individual regression models. So you split based on which category you're in, women or not, and then greater than 1985 or not, and in each leaf then you fit an individual regression model. Okay, that's cool. That works pretty well. And you don't have to be continuous everywhere, right? You actually, by virtue of there being these splits, you can have individual trees representing the regression function in all of the leaves, right? Which split up space, just like before. We can do density estimation like we did before and model the joint distribution of X and Y. That way, and 440. We can do non-parametric models. We can do k-nearest neighbors regression, right? So if we find the k nearest neighbors of this point, maybe 2 over here and 2 over here, and we take the average of their corresponding y values, and that's the output. That's kind of cool.
Do the domain of each leaf need to be continuous?
Back here, yes. If we're doing regression, that makes sense, right? What you'll realize sooner rather than later is that basically regression and classification are the same thing. They just have different losses. So regression trees, classification trees, they're kind of the same thing. They just have different losses and different split criteria in this particular case, right? Okay. So you can weight in these k-nearest neighbors regressors by distance. So close points get more weight, right? So closer points here get more weight. Whatever, it's easy. And you can weight and average over all the data. This is now this is basically a non-parametric model then, right? You can do locally linear regression where you fit a regression model at every single point and then average between those regression models, right? So you basically fit a linear model with the data weighted by distance. And this generally has better extrapolation than does the kind of thing we're talking about. And you can do ensembling just like before. You can improve average by averaging across regression models, okay? Not a big deal. And there are lots of applications for these kinds of things. But the critical thing is, here, we're going to focus on linear models with nonlinear transformations. And these are building blocks for more advanced methods, okay? So this is what we want to think about. And this is where, for some people, this is kind of for some people, this is the first time they they think about this. And the first step of this is to look at this and say, okay, we said we're interested in linear models, not affine models. This is an affine function, right? But we're definitely interested in regression functions that don't have to go through the origin. That's kind of dumb, right? So as it is right there, if xi equals 0, if our input is 0, then yi has to be 0. Okay, that's not what you want, right? Cool. So what do? We want to have this intercept term, this w naught. We want to be able to be away from the origin at when our feature is 0, right? If we add an intercept, that fixes it, right? That's what we want. Now there's a simple trick, and we're going to use this throughout. Deep neural networks use this all over the place, so on and so forth, and it's worth paying attention to. And we're going to introduce some new notation at the same time that we're going to use throughout the remainder of the course as well. Okay. There's a simple trick to add a y-intercept or bias variable here, which is to make a new matrix Z with an extra feature that is always 1. This is like really dumb, and super easy, but it gets the job done. Okay. So here's our original data x, right? N by 1, right? Now we're going to make a new matrix Z, which is going to be n by 2, and the first column is just going to be 1s. Okay. The second column is a verbatim copy of x. Okay. Now we do linear regression using Z. And just to make things a little bit clearer, we're going to use V instead of W as the regression weights when we use the features Z. Okay. So we're going to form our prediction. Y hat I is going to be V1 Zi1 plus V2 times Zi2. Okay. But of course, V1 is just W naught. Zi1 is 1. V2 is W1, and Zi2 is Xi1. Okay. Which is just W naught plus W1 Xi1, just as we want. So we get our intercept term for free by having this column be all 1s. Okay, cool. So we can have a non-zero y-intercept by changing the features, right? So we're going to expand our feature set, right? And now we have a different kind of polynomial function. It's a polynomial function with degree 1, but it also has degree 0 in it. Okay? That means that we can ignore the y-intercept in our derivations, which is cleaner, and it actually makes it obvious that it's linear regression because the function has this form, right? And not some intercept form, and not because the relationship that it's modeling is linear. Okay. So in many situations, right, as we saw in the 1985 drug fiasco data, right? Yi is not a linear function of xi, right? So, here's yi up here and xi is down here, and this is our plot, right? If we fit this with linear least squares, right? Not so pretty, right? Not the result that we would look for. Think of n-comes quartet. You're going to be fitting models, and it's not. We know that the relationship is nonlinear, but the function family that we're going to use to fit it can still be linear, right? Or at least this is what we're going to talk about. So the real question is, can we use least squares to fit nonlinear models? Payman, can we do that? Let me remove models here and say relationships.
We can split into multiple.
I'll ask the class as well, since Payman was probably watching some sort of soap opera instead of paying attention to the lecture just now.
No.
So
I
what do you
think
think?
we can maybe split our nonlinear model into multiple linear. That's what I.
So can we do it? If we
Sure.
split the data into linear pieces, we could. Okay, we've got just a pure yes from Shonik. Well, that's a good guess, right? Transform the data, something I don't know. Yeah, okay. Yeah, okay, great. So this is kind of the jumping off point, and it's yes from Juan. Okay. Can we fit data this way? I mean, obviously the slide titles are a little bit of a hint, right? You can do this by changing features. And this is a very powerful idea, and it's this idea arguably forms the basis for modern machine learning, basically. Right? So getting this in your head properly is a really good idea. Okay, so here's our X matrix as before. Okay, this is the bias or intercept term or whatever. Okay. Here's our Z matrix. We've got our X to the 0 column. Now we're going to have our X to the 1 column, and we're going to have our X squared column. And note, this is like, this is notationally crappy, right? This is notationally crappy as well. What we mean is we're going to take every individual value and square it. So we're going to distribute the square. So it's like the square operates on just add more columns. You got it. Yeah. Okay. All right. But now, as soon as you get this in your head, you just start adding more columns. Obviously, you can add the X cubed column, to the X. Well, okay, where do you stop, right? Okay, how flexible can you make it? And you can start to see straight away that as you add columns, D could possibly, yes, Baran, there you go. So you can make D really big if you want to, right? Okay, and why stop with polynomials? You can put sine of X here and cosine of X and exp of X and 1 over X, and what, like, you can come up with, yeah, exactly. Okay, so we're still going to do the exact same thing. We're just going to fit a linear. We're going to use least squares, right? We're going to do, we still have a linear model, but the relationship that we're going to model is a nonlinear relationship. Okay, so it's a linear function of W, but the relationship is a quadratic function of X. Okay, and that little in your head, if we can get it to happen, is maybe the most important thing that we do in modern machine learning, because neural networks are basically computing a change of basis. Our unsupervised learning techniques that we're going to talk about before we get there are okay. We're going to basically build feature sets for linear regression. So how do we do this with data sets with more than one feature? If you're saying that xi is more than one dimension, I think that's a good question. We haven't talked about that. We will talk about that. But you could imagine so we're just still talking about one-dimensional input, right? But if we had two-dimensional input, then the question is like what, we'll get there in a lecture or two, but just to foreshadow, right? You can have x I1, xi1 squared, xi1 times xi2, xi2 squared, right? Okay. If your original feature space it has more dimensions than just one. We're just talking about one-dimensional right now, and thinking about how to actually fit a nonlinear relationship in that case, right? So, yeah, so here in this particular case, zi1 is 1, zi2 is xi, zi3 is xi squared. So what you're actually fitting are the parameters of a second order polynomial when you use this feature space, okay? So cool. Linear least squares in our original data space gives you just a line. But when you do the transformation that includes the polynomial feature expansion, then you can learn nonlinear, and in this particular case, quadratic input-output relationships. Okay, and you have to think about that just a little bit, because like the extrapolants here are very, very different, right? Right. Okay. This would have a negative and a positive extrapolant forever. Now this is positive, positive, right? And maybe that's actually appropriate for your domain. Right? Maybe you know that, right? And it should be clear that our program, the program that we end up writing, right, we're going to learn these values v, right? But our program also has to have the ability to go from x twiddle to z twiddle. So to predict on new data x twiddle, we have to keep around this whatever basis expansion we apply. We need to have that at the beginning of our out of sample prediction module as well, right? Okay. So there was a hint in the chat channel about the fact that yes, you know, the degree of the polynomial can grow. And then it's sort of the obvious questions are like, how do you choose the degree of the polynomial? Like, can you overfit? All this sort of stuff comes to the fore again right away, right? And one of the answers is, of course, you use cross-validation to decide the polynomial order, right? Held out data, so on and so forth. That's the answer to that. There are polynomial basis functions that are numerically nicer, they're like Lagrange polynomials, so on and so forth. But we're just gonna deal with polynomials that look like this. Tobias, yes, this is like polynomial interpolation, yes. So in summary, we introduced matrix notation for expressing least squares problems. We introduced the normal equations, which is super important, which is the solution or gives the solution of the least squares problem as a linear system. Basically, if you solve this for W, then we're done. The solution might not be unique because of collinearity, but any solution is optimal because of convexity. We'll talk about this later, don't worry about it now. We hinted that you can do tree or probabilistic non-parametric ensemble tree regression methods, basically in response to the fact that maybe the input-output relationship is non-linear. And then we talked about nonlinear feature transformations, which allow us to model nonlinear relationships with linear models. And that's it for today. So if there are other questions, let's have it. Otherwise, thank you for your time. Oh, yeah. It's a dumb story, but it's like minor geek funny. We had this iClear deadline, and I don't know if you've noticed, I've always said that I can't really tell the difference between the slide background colors when it's on my monitors and I'm talking, right? So I was always worried that you couldn't see it at home when it goes from white to like, you know, puke colored background, right? And it turns out that the two new 4K monitors that were purchased for my group and distributed to all of my grad students come with a default setting that boosts all of the colors really, really, really bright. And while I was writing a paper, I had like a 25-minute back and forth with one of my graduate students, basically yelling at my graduate student, like, you changed the plot. There's a gray background that's missing. I can't see it anymore. What is going on? Like, you can't do that like an hour before the deadline. Like, what are you doing? He's like, it's there. I had to take pictures of my monitor and send it to him. I'm like, I'm not crazy. It's not there. And he's like, it is there. He's like, why don't you try sliding it over onto your other monitor, your normal laptop monitor? I'm like, oh, it's back. So it turns out that I can see the tan background. Like there's a UBC wide network outage, which means that I cannot actually use my monitors because they're on the same device as my wired connection. So I have to use my monitor today, like my just laptop monitor, and like I can see the slide background just like before. So yeah. Anyway, dumb, but you know, it was it's geek funny. It's fine. Kihong, do we need to know how to do regression with tree or probabilistic, or you just need to know that it's possible to do these. We might be really evil and ask you to do something like that on an exam as like an extra credit thing or something like that, but no, that's not your. If it's tan, it's going to be extra credit. Baran, do we get 4K monitors? You can if you pay for them yourself, no problem. It's easy. I can give you the Amazon link. Yeah. Cool. No other questions? No such thing exists. I can call up Alex Mola, but that's about it. Ilias, for machine learning, absolutely yes, 100%. Get it out of the way while you can. Yes, take a measure theoretic-based probability class, no question. If you're going to do probabilistic machine learning, it's really, really, really helpful in the end. You won't use it, but well, okay, 25% even in research you'll use it, but you'll understand way, 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 way more. You're welcome. All right, thank you all. Have a lovely evening. Thanks, Peyton.
Thank you very much. Bye.
Cheers.